Now that we know the magnetic flux, we can evaluate its time derivative. We need this because, remember, the induced EMF is equal to the time derivative of magnetic flux, and we need to know the induced EMF in order to determine the induced current in our loop. And let's re-add the depiction of that induced current into our sketch. So the time derivative of the magnetic flux, well, we have a bunch of terms here, but really all of these terms with respect to time are constant. So let's go ahead and write them outside of the derivative operator. So we have all of these terms, and then we have the time derivative of e to the minus t over rc. When we evaluate this, we just need to take the derivative of that exponential. And when we do that, our expression for the time rate of change of magnetic flux says that we have mu naught over 2 pi times the ratio of the potential difference of the initially charged capacitor over the resistance of our RC circuit times L. And when we evaluate the derivative of the exponential, we're going to get a minus 1 over RC. I'll put the minus sign out in front, and we have the natural log of A plus W over A, and this is e to the minus t over rc. Now that we have this expression for the time rate of change of magnetic flux, we could return to the expression we have for the induced current in the loop. And the expression we had for the induced current in the loop said that it is equal to minus 1 over the resistance of the loop times the time rate of change of magnetic flux. This means that our induced current in the loop is equal to minus 1 over the resistance of the loop, and the time rate of change of magnetic flux is equal to minus the permeability of free space over 2 pi times the potential difference over R, L over RC, natural log of A plus W over A, and I'm going to have to squeeze in this exponential e to the minus t over rc, and this is the expression we have for the current in our loop. Okay, so we have quite the nasty looking expression. So we have a minus times a minus, which is a positive. We have an r times an r, which will be an r squared. And we could probably do a couple more things by expressing some variables in terms of others, but I won't do that at this point. For now, I'll just go ahead and rewrite this line, hopefully for the last time, because we've been writing it a lot. So this is 1 over the resistance of the loop times mu naught, the potential difference of the initially charged capacitor, L over R squared C, and we have a 2 pi down here, natural log of A plus W over A times e to the minus t over RC. We are now ready to plug in numbers into this expression. We'll begin with the resistance of our conducting loop. We were told that that was equal to 0.050 ohms. This is followed by the permeability of free space, which is 4 pi times 10 to the minus 7 Tesla meters per amp, multiplied by the potential difference of the initially charged capacitor, which is 20 volts, times the length of our conducting loop, which is 2.0 centimeters. This is divided by 2 pi times the resistance of the resistor in our RC circuit, which is 2.0 ohms. This quantity is squared, times the capacitance of our capacitor, which is 5.0 times 10 to the minus 6 farads. This is times the natural log of the distance away from our loop, which is 0.5 centimeters, plus the width of our loop, which is 1.0 centimeters, divided by the distance away from the conducting wire, which is 0.5 centimeters. And this is multiplied to the exponential e raised to the minus t for time. Well, the time is 5.0 microseconds, and this is divided by the product of the resistance and the capacitance. Well, the resistance is 2.0 ohms, and the capacitance is 5.0 microfarads. Okay, we have a lot of stuff here, but I think we could do some simplification. Let's start with our exponential term. Now notice we have a microsecond over a microfarad ohms. Well, remember that product comes from RC, and you might remember that the product of RC has units of seconds. So an ohm farad is a second. So we have a microsecond in the denominator canceling with the microsecond in the numerator, and a 5 in the numerator canceling with a 5 in the denominator, leaving us with an exponent that's equal to minus 1/2. Now, if I'm working from right to left, I guess, since I started with the exponential, let's look at the argument of the natural log. So we have centimeter in the numerator cancels with a centimeter in the denominator, and we have a 1.5 divided by 0.5. The result here is 3 as the argument of the natural log. So natural log of 3. And then continuing our move, now in no particular order, I see that a pi in the numerator can cancel with a pi in the denominator. A 2 in the numerator cancels with a 2 in the denominator. A 4 in the numerator cancels with a 2 squared, which is 4 in the denominator. So rewriting this, we have the induced current in the loop is equal to 1 over 0.050 ohms times 1 times 10 to the minus 7 Tesla meters per amp times 20 volts times 1.0 times 10 to the minus 2 meters over 1 square ohm times 5.0 times 10 to the minus 6 farads. And this is the natural log of 3 e to the minus 1/2. When I plug this into my calculator, I get that the induced current in the loop is equal to 0.05 amps. And you should double check the units. You know, we have a Tesla, some meters, some amps, some ohms. Double check the units as an exercise. But the result I get is that the induced current in the loop is equal to 0.05 amps in the counterclockwise direction.